Some nights the sky holds a kind of stillness that feels almost deliberate, as though the darkness itself has settled in gently, the way a heavy blanket does slow and sure over everything beneath it. If this feels like a good place to rest tonight, you are welcome to stay. Now, let's drift. There is something the night sky has always kept quietly to itself, something that most of us sense without quite knowing why when we look up long enough and let the looking go soft. The stars are there. They have always been there. And yet what you are seeing right now in this moment is not the stars as they are. It is the stars as they were, light years ago, decades, centuries. In some cases so long ago that the star itself may no longer exist at all. You are looking at the past, and the past is looking back at you still glowing. Astronomers have known this for a long time, though knowing it and truly feeling it are two different things entirely. Light travels at a speed so vast it becomes difficult for the mind to hold nearly 300,000 kilometers every single second. And still across the distances of space, even that speed is not enough to make the universe feel close. The light reaching your eyes from the nearest star beyond our own sun, a faint quiet star called Proxima Centauri, left its source more than 4 years ago. 4 years of travelling through the cold and the dark before it arrived at this particular window on this particular night where you happen to be resting. It has been waiting in a sense, moving toward this moment for longer than you may have been thinking about it. The stars that seem a little brighter, a little steadier, those may have sent their light a few hundred years back, and the ones that appear as the faintest suggestions at the edge of vision, the ones you can almost only see by not looking directly at them, researchers have found that some of that light began its journey before recorded human history, before language, before any hand pressed any mark into any stone. There is something profoundly soft about that if you let yourself sit with it for a moment. The sky then is not a ceiling. It is more like a depth, a layering of times, all arriving at once, all meeting in the same quiet moment above you. The light from one star tells you something about a world that existed 200 years ago. The light from another carries news of a place that existed 1,000 years before that. And they arrive together without urgency, without any particular order, pooling gently into the same dark, above the same small town, the same rooftop, the same open field. Scientists sometimes describe this as looking back in time, but it might feel more accurate at this hour to think of it as being visited by old light, by patient light, by light that has survived unimaginable distances of cold and silence and arrived here softly to rest on your window. Now there is something else worth knowing, something that sits just beneath that first layer of wonder. The stars you see tonight are not all the same age. They are not all at the same stage of their lives. Some of the ones you can see, the bright, familiar ones, are young, geologically speaking, still burning with the particular energy of something new. Others are ancient in ways that make the word ancient feel small. Red and dim and slow, they have been burning for so long that the universe around them has changed almost beyond recognition since they first ignited. And all of them, every single point of light you can see or imagine, every one of them is burning something to do it. Stars do not shine because they are permanent. They shine because they are spending themselves, fusing hydrogen into helium in their cores, releasing energy in the form of light and heat moment by moment through billions of years. The light is real, the warmth is real, but it is at its heart a kind of slow expenditure, a giving away. It may be that this is one of the quiet truths the night has always been holding, that light is not a state of being, it is an act, and every act has somewhere in its nature an end. This is not a sorrowful thought, not at this hour, not the way you are receiving it right now. It is simply the shape of things. The way water moves, the way breath moves, the way seasons move without being asked to. The universe has been doing this for so long that the rhythm of it has become in some sense the background music of everything. Studies in astrophysics have long noted that the universe we inhabit is not a static place. It is moving, expanding still from whatever beginning gave it shape, cooling slowly in the spaces between things, and filling still with light, though that filling is not infinite. The stars are forming more slowly now than they once did, far more slowly. The great burst of star formation that lit the early universe has quieted the way a busy room quiets after most of the people have found their place. The universe is still full of stars, more stars than there are grains of sand on every beach on this planet, a comparison so often repeated that it has lost some of its power, and yet it remains true and worth sitting with in the dark when the mind is soft enough to let the scale of it land without effort. But the forming of new ones has slowed to something like a murmur. Researchers have described the current period of cosmic history, the period we exist within, as the stelliferous era, the age of stars. It began not long after the universe itself, when the first hydrogen clouds collapsed under gravity and ignited, and it will last for trillions of years to come. By human standards, this era is unimaginably long. We are nowhere near its end. Our sun is middle-aged roughly. The stars above you tonight are in cosmic terms very much still here, and yet the direction is set. The arc is visible if you know where to look and how to look slowly. The universe is not expanding its brightness. It is maintaining it for now, in the particular way that all things maintain what they have before the long releasing begins. It is like a breath held very gently, steady, present, but held. You tonight are living in the lit part of the universe's story, the part where looking up still means being met with light, where on any clear night from nearly anywhere on the surface of this small and fortunate planet, you can tilt your head back and be surrounded by evidence that the universe is still actively quietly burning, still offering something to the dark. That is not a small thing. It may be that most of us move through our days without quite registering what we're standing inside of. This era, this particular window in cosmic time, a window that opened slowly billions of years before any eye existed to see through it, and that will close just as slowly long after anything resembling us has gone quiet. But right now tonight the window is open, the stars are out, and some of their light has travelled almost incomprehensibly far to be here to arrive without announcement, without fanfare through whatever small opening exists between you and the sky, through a window, through a skylight, through the remembered image of a clear night held somewhere softly in the back of the mind. The brain neuroscientists have found responds to starlight differently than it does to artificial light. Not dramatically, not in ways that feel sudden or striking, but quietly. The quality of darkness around natural light sources registers differently, somewhere deep in the brain's older structures, the ones that were calibrated long before electricity existed, long before any source of light that didn't come from fire or stars or the slow brightening of dawn. There is something in the nervous system that recognizes a night sky as safe, as correct, as the right kind of darkness, the kind that has always been there, that will always return. That means nothing is wrong. You may feel a version of that now if you let yourself. The particular calm of knowing that the darkness is full even when it looks empty, that the light is still there even when it seems far away, and it is far away. That is one of the quiet miracles of all of this. The stars are so far away that their light takes years to reach us. Some of them have changed, burned brighter, dimmed, shifted, and we will not know for centuries. We are always receiving the past, always living in the afterglow of something that happened long before we were aware of it. Perhaps that is why the night sky has always felt to so many people like something that does not need to be solved, It asks nothing of you. It does not require understanding in order to be beautiful or to be felt. It simply is vast and patient and quietly full of things that have been travelling toward this moment for longer than the mind can comfortably hold. And in that travelling, in that patient arriving, there is something that feels, even if you cannot quite name it, like a kind of companionship. The light is old, the dark between it is older, and both of them together have been making the kind of silence that is not empty but full and steady and almost kind. There are more layers to this waiting just ahead. The stars themselves have stories how they are born and how they live and what it costs them to shine. And somewhere in those stories is something that may surprise you with how familiar it feels. For now, though, let the sky be what it is. Old light and new darkness arriving together, settling around you like everything that doesn't need to be hurried. Part 2, How a Star is Born and Why It Cannot Last. Word count 1,800. Duration 12 to 14 minutes. Somewhere in the universe right now, in a region of space so distant that its light has not yet reached us, and may never reach us in any lifetime, we can imagine a star is being born. It is not a sudden thing. It is not a flash or a spark or anything that would register to a watching eye as a beginning. It is slow, profoundly, almost tenderly slow. The kind of slow that makes a human life feel like a held breath by comparison. It begins with a cloud. Astronomers call them nebulae, vast regions of gas and dust drifting through the space between existing stars. Mostly hydrogen, some helium. Traces of heavier elements left behind by stars that lived and ended long before this particular cloud began to stir. These clouds are enormous in ways that resist easy imagining. Some of them span hundreds of light years across, meaning that light itself, travelling at its full and extraordinary speed, would take centuries to cross from one edge to the other. For a very long time, these clouds simply drift, slowly rotating, cooling, occasionally disturbed by the shock wave of a distant stellar explosion, or pulled gently by the gravity of something passing nearby. They are patient in the way that only very large, very cold things can be patient without knowing they are waiting, but waiting nonetheless. And then at some point in some region of the cloud where the density has grown just a little too heavy to hold itself apart, something shifts. Gravity, that quietest and most persistent of forces, begins to win. The cloud starts to collapse inward. Not quickly. Over thousands, sometimes millions of years, the gas and dust at the densest part of the cloud falls toward a common centre. As it falls, it compresses. As it compresses, it heats. The physics here is something we understand quite well. Evidence suggests this process follows the same principles, whether it happens in a cloud near our own galaxy, or in one so far away we have no name for it. What we understand so far suggests that as the collapsing core grows hotter and denser, it begins to rotate faster the same way an ice skater pulls inward and spins. The surrounding material flattens into a disk, and at the very centre something is forming that is neither fully star nor fully cloud. A protostar still gathering itself, still pulling in mass from the disk around it, growing warmer with every passing 1,000 years. This stage can last for hundreds of thousands of years. A star in the making, not yet making light in the way we would recognize it, just glowing dimly in the infrared hidden inside its cloud, warm and dense and not yet ready. And then when the core has grown hot enough and dense enough and the pressure at its center reaches a threshold that took the entire previous process to build fusion begins, hydrogen nuclei pressed together with enough force to overcome their natural repulsion merge. They become helium, and in that merging a small amount of mass is converted directly into energy, not burned the way wood burns, something more fundamental than that. Matter itself becoming light. This is the moment a star is born. Not with any sound, not with any announcement, just a sudden new brightness somewhere in a cloud, a warmth where there was only cold, a presence where there was only potential. It is, researchers have found, one of the most common events in the universe. Stars have been forming this way for most of cosmic history. They are forming right now in clouds we can observe with modern instruments, at rates that, while slower than the early universe, still represent something almost beyond counting. And yet each one is its own event, its own particular collapse, its own particular ignition, its own particular beginning. Our Sun began this way roughly 4.5 billion years ago. A cloud in one of the spiral arms of what become the Milky Way grew dense enough, collapsed far enough, heated enough at its core to begin fusing hydrogen. The disk of material surrounding it slowly gathered itself into planets, into this planet among others, into the ground beneath every house, every field, every ocean floor, into the calcium in every bone, into the iron in every cell of blood. Everything you're made of was once part of that original cloud, and the cloud itself was made of the remnants of stars that came before stars that lived and ended, billions of years before the Sun ever formed, seeding the galaxy with the heavier elements that simpler stars could not produce. You're in a very literal and astrophysical sense the product of multiple stellar generations. Not one star's legacy, but many. A kind of inheritance passed forward through explosion and drift and collapse and ignition, over and over across timescales that make the word ancient feel newly humble. But here is the thing that sits quietly at the center of all of this, the thing that the beauty of stellar birth does not immediately ask you to notice. A star begins its life spending itself. The moment fusion ignites, the star begins consuming its hydrogen. Slowly at first, steadily. For a small star, the process can last for billions of years, tens of billions even. For a massive star burning hotter and brighter, the supply runs through much faster. Millions of years for the very largest ones, which is in cosmic terms a rather brief existence. The light we see is not a surplus. It is not something a star has to spare. It is the direct result of the star converting its own substance into energy, releasing through each fusion reaction a fraction of itself as light and heat and radiation that then travels outward through space until it lands eventually on something. On a planet perhaps, on an ocean, on a face turned upward on a warm afternoon. It may be that all light, when understood, fully carries this quiet quality, that it is not simply emitted but given, that every photon that has ever warmed anything was once something else converted by pressure and heat, and time into the only form in which it could travel freely through the universe. Stars do not know this, of course. They do not experience their own burning any more than a river experiences its own movement. The physics simply unfolds as physics does without commentary. But something about knowing it, something about holding the image of a star as a thing that gives itself away steadily and completely over the course of billions of years, changes the quality of looking up, at least a little, at least at this hour when the thinking mind is slower than it usually is, and things have a way of landing differently. The life of a star from its beginning to its end is called its stellar evolution, and the path it takes depends almost entirely on one thing: how much mass it started with. This single initial quantity, the amount of material that fell into that first collapsing core, determines almost everything that follows. The temperature it will burn at, the color it will glow, how long it will last, how it will end. A star like our Sun, a medium mass star, neither the largest nor the smallest, will spend the bulk of its life in what astronomers call the main sequence, a long, relatively stable period during which it fuses hydrogen at its core at a more or less steady rate. This phase for our Sun has been ongoing for roughly 4.5 billion years, and it may continue for another 5 billion more. A 10 billion year lifespan, give or take. Unhurried, consistent, the kind of long, quiet labour that sustains rather than dazzles. Stars more massive than our sun burn their fuel faster and hotter. They shine brilliantly. The bright blue-white stars that stand out even in a crowded sky are often of this type, but they pay for their brightness with brevity. Some of the most luminous stars known to us may last only a few million years before reaching their end. And then there are the small ones, the quiet ones, the ones that do not make much of an impression at first glance. The smallest stars, the red dwarfs, are not much to look at by stellar standards. They burn cool and dim, a deep reddish hue rather than the yellow-white of our sun or the fierce blue-white of the massive ones. They are misers with their fuel in the best possible sense, fusing hydrogen so slowly, so carefully, that their lifespans extend not into the billions of years but into the trillions. Scientists suggest that the most long-lived red dwarfs may burn for 10 trillion years or more. 10 trillion. A number so far beyond our ordinary experience of time that it asks something of the imagination simply to hold it gently, without forcing it into a familiar shape. Our sun will have been gone for billions upon billions of years before some of these small stars even reach middle age. There is something almost comforting in this. The universe, it turns out, is not in a hurry. It contains within it forms of patience that make our own sense of long and short feel like something drawn on a grain of sand with a fingernail. It is patient in ways we have barely begun to measure. It saves its longest burning for its most modest flames. And all of this, the birth and the burning and the long, slow spending of a star's life, is happening right now in every direction from where you are lying. Not in metaphor, not as a way of speaking, actually happening in real places, in real clouds of gas and real collapsing cores and real nuclear fires, burning at temperatures our instruments can measure, but our bodies can barely conceptualize. The sky is not decorative. It is not a backdrop. It is a process, a living, ongoing, extraordinarily ancient process, and you are inside it, not outside it looking in, but inside it, made of it, resting within it. The mind quietly registers this even when we do not ask it to. Something in the awareness of a clear night sky has always known it was looking at something more than scenery, something more than stillness. Some older part of the brain researchers have found responds to open sky the way it responds to very little else, with a particular kind of quiet. A loosening. As though the body remembers, even when the mind has moved on to other things, what it is to be small in a large space and safe. A star is being born somewhere right now, slowly, without hurry. A cloud is collapsing. A core is heating. A process is beginning that will last for billions of years and produce light that may travel across distances we have never named toward places that do not yet exist. And a star somewhere is reaching the end of what it has to give. Not suddenly, not dramatically, but quietly running low the way a fire runs low in the hours before morning, still warm, still present, still casting its light, but moving gently and inevitably toward a different kind of quiet. What happens when that quiet finally comes, what a star becomes in the long aftermath of its burning, is a story that unfolds in ways the universe keeps surprising us with. Ways that are stranger, and in some respects softer than you might expect. The path from light to darkness is not a simple one. It takes many forms, and some of them are worth sitting with here in the dark for just a little longer. Part 3. The universe is already dying very, very slowly. Word count 1950. Duration 13 minutes. There is a word that astronomers use quietly among themselves when they talk about the long future of everything. The word is cooling, not ending, not dying exactly, not in the sharp, sudden way the word dying usually implies. Just cooling, the way a room cools after the people have left it. the way stone cools after a long summer day, slowly releasing its warmth back into the air, into the dark, into the particular stillness of a night that has no particular interest in hurrying. The universe, it seems, is doing something like that, has been doing it in fact for a very long time, and most of us move through our lives without ever knowing that the sky above us, vast and full, and blazing with the light of hundreds of billions of stars, is in the gentlest possible sense already on its way towards something quieter. To understand this, it helps to go back. Not far, not to the beginning, not to the first seconds of everything which belonged to a different kind of story. Just back far enough to see the shape of what has already happened. In the early universe, roughly 10 billion years ago, stars were forming at a rate that would be almost unrecognizable to us now. The raw materials were abundant, vast clouds of hydrogen, denser and more plentiful than anything that drifts through space today, and gravity had not yet used most of them up. Galaxies were young and turbulent and bright with the blue-white light of massive, newly ignited stars. The universe was in the language of cosmology productive, actively, exuberantly making things. Researchers have found that this period of peak star formation is sometimes called cosmic noon, the high point in the universe's history of turning gas into light. A time when the cosmos was building itself most enthusiastically, most abundantly, most rapidly. That period has passed. It passed slowly. That is important to understand because nothing in this story happens quickly. Cosmic noon did not end the way a day ends, not with a single moment when the light shifted and something changed. It faded. Over billions of years, the rate of star formation began to decline. The raw material was being used up. The densest, most productive regions of gas had already collapsed into stars, into galaxies, into the complex structures we now inhabit. What remained was less concentrated, more diffuse, harder for gravity to gather into something new. Scientists suggest that today, right now in this particular era of the universe's life, new stars are forming at roughly 1/10 the rate they were at cosmic noon. 1/10. The universe is still making stars. Our own galaxy produces a handful of new ones every year on average, scattered through the slow-moving clouds of the Milky Way. But the pace has changed. The urgency, if a universe can be said to have urgency, has settled. What we're living through, astronomers quietly note, is the long, gradual dimming that follows the peak. Not darkness, not yet, not for a very long time, but the beginning of the arc that leads there. The universe is past the brightest point of its story. The stars above us tonight are the inheritance of a more luminous time. This is a thought that could feel heavy if you held it the wrong way, but there is another way to hold it softer, more spacious, and it goes something like this. We exist in the middle of the story, not at the beginning when everything was new and raw and forming itself out of chaos, not at the end which is so far away that the word far loses all meaning, but here, in the lit part, in the long inhabited middle when the universe is old enough to have made something as intricate as a nervous system, as old as a civilization, as small and specific as the particular quiet of this particular night. The light we have is borrowed in a sense from a more luminous past, and it is still here. That is worth noticing. The era we inhabit has a name in the cosmological timescale that physicists use to map the deep future. It is called the stelliferous era, from the Latin for star-bearing, star-carrying. The age in which the universe is still populated by active stars still lit from within by the ongoing process of nuclear fusion, still warm enough in the right places for chemistry to work, for water to exist in liquid form, for the particular conditions that allow something like awareness to arise and look up and wonder about what it is looking at. The stelliferous era began not long after the universe itself, within the first few 100 million years, as the first stars ignited from the primordial gas. and it will last evidence suggests for somewhere around 100 trillion years in total. A number so large it has to be released rather than understood. 100 trillion years. Our entire universe as we currently know it is only about 13.8 billion years old. The stelliferous era has barely passed its opening chapters, and yet the direction is set. The rate of star formation is declining. The raw materials are being used up and not replaced, and at some point in the unimaginably distant future, the last new star will form. The last cloud of gas will collapse slowly into the last ignition. And after that, no new stars. Only the ones already burning, living out whatever remains of their individual lives one by one, growing dimmer one by one, going dark. What we understand so far suggests that the stelliferous era will end not with any single event, but with a gradual thinning of the light. The most massive stars which burn fastest will go first. They are already gone, many of them. The blue giants that blaze through the early universe have long since exploded and left their remnants behind. The medium stars like our Sun will follow over the next several billion years. And last of all, persisting long after everything else has gone quiet, will be the red dwarfs. The smallest, coolest, most patient of all the star types, burning so slowly that they will still be here when the universe is 1,000 times its current age. There is something almost comforting in that in a way that is difficult to fully explain. The idea that the last light in the universe will be small, quiet, the kind of light that would barely be visible from a distance. Not a blaze, not a finale, but a low and steady glow continuing simply because it has not yet run out of what it needs to continue. The last star will not know it is the last. It will simply burn as it has always burned in the way that all things do what they do, without requiring an audience or a meaning. It may be that this is one of the things the universe does most consistently across all of its scales and all of its time scales. It simply continues until it doesn't. Without drama, without announcement. The continuing is the thing. The burning, the cooling, the slow release of energy into the space around it. This is what the universe is at its most fundamental. Not an event, a process, long and quiet and indifferent to whether any part of it is witnessed, and yet here we are witnessing it, or the small lit edge of it at least, looking up at a sky that is by the standards of what is coming extraordinarily bright, alive with the light of hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies beyond that, each with their own hundreds of billions of stars, each burning at their own pace, each somewhere in their own arc between ignition and quiet. The scale of it is as always something the mind reaches toward and then releases. But the reaching is worth something. The quiet attempt to hold it even briefly, even softly before letting it go. Cosmologists who study the deep future of the universe, and there are people who spend their lives doing exactly this, sitting with the very long view, sometimes describe the stelliferous era with a particular kind of affection. Not sentimentality exactly, more like the feeling of recognizing that you're inside something finite and not taking that lightly. Because the universe, for all its scale, for all its billions of years of past and trillions of years of future, is not doing this forever. The stars are not a permanent feature of reality. They are a phase, a long, beautiful, light-producing phase in the life of a universe that began without them and will eventually end without them. We are in the middle of that phase, the lights are on, the fire is still burning. And the only witnesses to any of it, the only things that have ever, as far as we know, stopped to notice that it is happening, are here on this small warm planet, in this small lit corner of a galaxy, that is itself a small lit corner of something almost too large to think about. It matters somehow that we notice, even softly, even at night when the thinking is slow and the mind is not insisting on conclusions. The universe is already dying very, very slowly, and it is still right now, tonight, extraordinary. Both of these things are true at once, and holding both of them without needing one to cancel the other is something that seems to come most naturally in the dark when the body is still, and the breath has found its own rhythm, and the mind is not trying to do anything with what it knows, except simply let it be known. The stars above you are burning, have been burning for billions of years, will continue burning for billions more. The universe is dimming somewhere at the far edge of the very long arc, and you are here in the lit part in the warm middle of something that will not always be this way. That is enough to rest with for now, and what remains after the last star finally fades is something scientists have only recently begun to name, and it is quieter and stranger and more patient than anything the universe has held before. Not all stars announce themselves. Some of them have been burning for longer than our solar system has existed, and you would never know it by looking at them. They offer no particular drama, no blue-white intensity that commands the eye across a galaxy, no swelling into giants, no spectacular deaths. They simply burn quietly, carefully, with a kind of dim and steady persistence that most of the universe seems not to notice. These are the red dwarfs, and in the long story of the universe they may be the most important characters of all, not because of what they do loudly, but because of how extraordinarily long they stay. A red dwarf is a star with a fraction of the Sun's mass. The smallest of them contain perhaps 8% of what our Sun weighs, just barely enough mass for the core pressure to sustain nuclear fusion at all. Any less, and the object becomes something else entirely, something that never quite ignites into a true star. But at this threshold, something remarkable happens. The fusion begins, and it runs not brightly, not quickly, but with a patience that defies easy comprehension. Researchers have found that the least massive red dwarfs may burn for 10 trillion years or more. To put that in some kind of relation to anything familiar, our Sun is approximately 4.5 billion years old, and the universe itself is roughly 13.5 billion years old. A red dwarf at the lower end of the mass spectrum will still be burning long after a period of time equal to 700 times the current age of the universe has passed. It has not been very long at all, in other words. For a red dwarf, we are very early in the story. Part of what makes this possible is the way red dwarfs manage their fuel. Unlike stars the size of our Sun, which burn through the hydrogen in their cores, and then exhaust that central supply, forcing the fusion to migrate outward, red dwarfs are what scientists call fully convective. This means that instead of burning through one region and leaving it depleted, they continuously circulate all of their hydrogen throughout their entire interior. The fuel mixes. The unused hydrogen from the outer layers cycles down into the core, and the processed material cycles back out. It is in a sense the most efficient possible arrangement. Nothing sits unused at the edges while the centre starves. Everything available gets used slowly, evenly over the longest possible timescale. Evidence suggests that this convective mixing is what grants red dwarfs their extraordinary longevity, not simply having more fuel, but using all of what they have with a consistency that larger stars never achieve. A red dwarf does not burn bright and leave reserves untouched. It burns modestly and burns everything across a span of time that makes even the word ancient feel approximate. Their light is dim and red, further toward the long wavelength end of the visible spectrum than our Sun's yellow-white output. If you were standing on a planet orbiting a red dwarf, the sky during the day would look different from anything we experience here. Not the blue of Earth's midday, but something warmer, deeper, a perpetual quality of late afternoon perhaps, or early evening, the light carrying more red and less blue than we're accustomed to. Some scientists describe it as a kind of permanent golden hour. Others note that it would depend heavily on the planet's atmosphere. The scattering and filtering effects of different gases would shift the perceived colour in ways that are difficult to predict precisely. What we can say is that the light would be softer, dimmer, less intense on the skin and in the eyes than the sun we know. It may be that there is something appropriate about that, the longest-lived stars offering the gentlest light. There are more red dwarfs in our galaxy than any other type of star, by a significant margin. Estimates suggest that somewhere between 70 and 80% of all stars in the Milky Way are red dwarfs. They vastly outnumber the sun-like stars that we tend to think of as typical, partly because we have built our sense of what a star looks like around the one we happen to orbit. But our sun, in the census of the galaxy, is not the norm. It is on the larger, brighter, shorter-lived end of a distribution that extends much further down toward the small and the dim and the patient. The galaxy, if you could see it in full, would be overwhelmingly populated by stars you would struggle to see with the naked eye. Faint red points scattered across the dark, burning carefully, each one a potential centre for a system of worlds, each one a slow, steady source of energy lasting longer than the mind wants to follow. The stars we romanticize, the brilliant ones, the ones that dominate constellation lore and ancient navigation, are the minority. Bright, yes. Visible, yes. But brief by the standards of what surrounds them. Red dwarfs have another quality that sets them apart from our sun, and it is one that makes their potential to host life a more complicated question than it might first appear. They are active, not constantly, not all of them, and not in the same way throughout their lives, but particularly in their youth. Red dwarfs produce powerful stellar flares, eruptions of radiation, and charged particles that burst outward from the star's surface with an intensity that can in some cases briefly outshine the star itself in certain wavelengths. These flares are not unusual events. For some young red dwarfs they occur multiple times per day. For a planet sitting close enough to a red dwarf to receive sufficient warmth, and the habitable zone around such a dim star is necessarily much closer in than Earth's distance from the Sun, these flares would be significant. The radiation environment would be intense, particularly in the early billions of years of the star's life. Atmospheres can be stripped, chemistry can be disrupted. Scientists are still exploring what this means for the possibility of life around red dwarfs. Some researchers suggest that life might find ways to adapt to shelter, to develop underground or underwater, shielded from the worst of the radiation. Others point to the sheer timescale available if biology can gain a foothold, and the star's activity eventually settles, as it does seem to settle. After the first few billion years, there is then an almost incomprehensible amount of time for complexity to develop. What we understand so far suggests that the question is genuinely open, and open questions at this hour are the best kind. There is something worth dwelling on very gently in the idea that the universe's longest-lived stars are also its most modest ones. A star 10 times the mass of the Sun burns with extraordinary brightness for perhaps 20 million years, then dies in a dramatic explosion that seeds nearby space with heavy elements and shock waves. It is spectacular in its way, generous even in what it leaves behind, but it does not last. A red dwarf with 1/10 of the Sun's mass produces almost no light you could see from a distance. It causes no supernovae. It enriches its surroundings with almost nothing. It simply continues for 10 trillion years, patient and dim and entirely consistent long after everything around it has changed beyond recognition. This is not a story with a moral. The universe does not arrange itself to teach lessons, but there is something in the observation, in the plainly physical fact that the longest-lasting stars are the quietest ones, that the mind can rest in for a moment without needing to interpret it further. Astronomers looking into the far future of the universe, tracing the arc of the stelliferous era toward its eventual close, find that the end of star formation will not be marked by any catastrophic event. No collision, no explosion, no singular moment of loss. It will simply be the point at which the last red dwarf forms from the last available gas cloud, and then there are no more. That red dwarf will then burn for trillions of years. Long after the Milky Way has merged with neighbouring galaxies and the combined structure has settled into something quieter. Long after our Sun has expanded, shed its outer layers, and cooled into a white dwarf no longer capable of warming anything. Long after anything resembling what we call civilization has either transformed into something unrecognisable or grown quiet entirely, the last star in the universe will almost certainly be a red dwarf. Small, dim, red, burning with the same patient consistency it has always known, and it will have no audience, no planets with eyes to observe it most likely, or if any remain, their surfaces will be cold and dark and entirely still, receiving only the faintest warmth from a star too old and too distant to make much difference. The universe around it will be nearly silent. The other stars will be gone. The galaxies will have dissolved or collapsed. The background will be cold. And still it will burn, because that is what it does, because the physics of it has not yet run out. There is a quietness to imagining that last red dwarf that feels different from sadness. It is something more like the feeling at the end of a very long and very full day when the last light in the house goes out, not because anything has gone wrong, but simply because it is time and the day has been complete. The universe will have had its stelliferous era, its hundreds of trillions of years of burning, of forming, of filling the dark with improbable light. And when the last small star finally dims, not with a bang, not with anything dramatic, but with the same slow, consistent fading that defines its entire existence, it will have been in its modest way the final act of something vast. The dim ones outlast the brilliant ones. The careful ones outlast the spectacular ones. The ones that burn slowly and share little and ask for no attention go on and on and on. Something about that truth is easier to receive in the dark with the mind going soft than it would be in any other light. And there is still more to this, because what happens after that last red dwarf fades is not simply nothing. The universe does not stop changing when the stars go out. It keeps going in ways that are stranger and harder to picture, and in some ways more interesting for being so far outside ordinary experience. What fills the dark after the last light is a kind of presence that has no name in any human language older than a century. And understanding it even softly, even just at the edges, changes something about how the darkness feels. Every star at some point runs out of something, not all at once, not suddenly. The process is long and internally complex, unfolding over millions or billions of years depending on the star's particular nature. But eventually the balance that has held the star together, that precise, extraordinary equilibrium between the gravity pulling inward and the fusion energy pushing out, begins to shift. The fuel that has sustained the fusion grows scarce. The outward pressure weakens, and the star, which has spent its entire existence in that careful balance, begins to respond. What happens next depends almost entirely on how much the star weighs, and the range of outcomes is one of the stranger things the universe offers to consider slowly in the dark. For stars like our Sun, middleweight, moderate, the unhurried kind, the end begins not with explosion but with expansion. As the hydrogen in the core depletes, the fusion gradually migrates to a shell of material surrounding the core. This shell burning generates more energy than the core fusion did, and the outer layers of the star, responding to this changed pressure from below, begin to move outward, slowly, over millions of years. The star swells. Researchers have found that a star like the Sun will eventually expand to perhaps 100 times its current diameter, possibly more, becoming what astronomers call a red giant. Its surface temperature will drop as it expands, shifting from the sun's current yellow-white toward a deeper, cooler red. Its luminosity will actually increase despite the cooler surface temperature, simply because the surface area has grown so enormously. From a distance, a red giant is a striking thing. Up close it would be something else entirely, a vast diffuse presence filling much of the sky of any nearby world, its outer atmosphere so thin it is barely more than a hot fog extending through space. Not a solid or a liquid, just energy and gas spread across a region where there was once a more compact, more defined source of light. The inner planets of our solar system, Mercury, Venus, and possibly Earth, will likely be engulfed during this phase. Not in a sudden catastrophe, but gradually as the sun's expanding atmosphere reaches outward over millions of years. The orbits of those planets may also shift as the sun loses mass during this process, complicating the picture further. Some models suggest Earth might migrate outward just enough to survive the expansion. Others suggest it will not. It seems that even the long-term fate of the world we live on carries a degree of uncertainty, not the uncertainty of crisis, but the gentler uncertainty of a story whose ending has not yet been fully written and will not need to be read for longer than the mind comfortably holds. What matters at this scale is not the specific outcome, but the nature of the process. A star does not end the way a fire ends abruptly, leaving cold ash where warmth was. A star ends the way a tide ends, or a season, or a very long conversation that gradually finds its way toward quiet. Slowly, with intermediate stages, with transformations along the way that are themselves remarkable. After the red giant phase, what remains of a sun-like star enters one of the most beautiful and quietly strange stages in stellar evolution. The outer layers, that vast diffuse atmosphere that has been slowly expanding for millions of years, eventually drift away entirely. They are released by the star's radiation pressure and the gentle stellar wind that has been blowing outward throughout the red giant phase, and they form what astronomers call a planetary nebula. Not because it has anything to do with planets, but because early observers with modest telescopes thought the glowing shells of gas resembled the disk-like appearance of planets in their eyepieces. A planetary nebula is in essence a star's outer self released, drifting outward into space in expanding shells and rings, illuminated by the intense radiation of what remains at the center, glowing in colors that depend on the chemistry of the gas greens, from doubly ionized oxygen reds from hydrogen blues from helium, or complex combinations of all of these. Photographs of planetary nebulae are among the most visually arresting images in all of astronomy, though at this hour the mind may prefer to simply hold the idea of them, rather than look for an image, vast, delicate, expanding rings of gas lit from within by the last energy of a dying star drifting quietly outward through space that is otherwise dark and cold. The gas will eventually disperse, spread across the interstellar medium, mix with other gas and dust, become in time the raw material from which new stars and new worlds are made. A star's ending in this way is also a beginning for something else, not in a sentimental sense, but in a purely physical one. The atoms do not stop existing. They change their arrangement, their location, their temperature. They find new configurations. They continue. What the expanding star leaves behind at its center after the outer layers have drifted away, and the planetary nebula has formed and begun to fade, is a white dwarf. This is the stellar remnant that most sun-like stars produce. A dense hot object roughly the size of Earth, but with a mass comparable to the sun's. The compression is extreme. A teaspoon of white dwarf material would weigh several tons. The temperature at formation is extraordinary, tens of thousands of degrees Celsius at the surface, cooling only slowly over billions of years, because there is so little surface area relative to the heat stored within. A white dwarf is no longer fusing anything. It has no internal energy source. It is in the strictest physical sense a cooling ember. The light it emits is the light of residual heat gradually releasing into the surrounding space over timescales that dwarf everything that came before. A white dwarf will take hundreds of billions to trillions of years to cool completely, far longer than the universe has currently existed. The mind tends to find rest in that particular fact without quite knowing why. Perhaps because it suggests that even after a star has finished its active life, it is still warm, still present, still radiating, however faintly, the energy of everything it once was. The more massive stars follow a very different path toward their endings, and where the sun's fate is slow and expansive and ultimately quiet, the fate of a star many times more massive is neither slow nor quiet. A massive star one with perhaps 8 times the sun's mass or more burns through its hydrogen rapidly, then proceeds through a series of subsequent fusion reactions that a sun-like star never reaches. After hydrogen runs low, helium fusion begins producing carbon. Then carbon fuses producing heavier elements. Then those fuse into still heavier ones. The star processes element after element in nested shells of fusion, each layer burning at higher temperatures and pressures than the last, working its way up through the periodic table in a sequence that takes only thousands of years once the later stages begin. Eventually the fusion reaches iron, and iron is where the sequence stops. Evidence suggests that iron is the element at which nuclear fusion stops producing energy. Fusing elements lighter than iron releases energy. That is the physics that powers all stars. But fusing iron requires energy rather than releasing it. When a massive star's core fills with iron, the outward pressure from fusion disappears and nothing replaces it. What follows is extraordinarily rapid by stellar standards. The core suddenly, without the pressure that was holding it open, collapses. In a fraction of a second, some accounts suggest as little as 1/4 of a second. For the actual collapse, a core the size of Earth compresses into a sphere roughly 20 kilometers across. The outer layers falling inward behind the core hit this suddenly rigid surface and rebound outward in a shock wave of almost incomprehensible violence. The result is a supernova. A supernova is the brightest event in the observable universe that is not another universe. For days or weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of suns. The energy released in the first seconds of a supernova is greater than the sun will produce across its entire 10 billion year lifespan. The shockwave travelling outward through the surrounding space compresses gas clouds, triggers new star formation, and seeds the interstellar medium with the heavy elements forged in the star's core: iron, nickel, gold, uranium, and dozens of others that could not have been produced any other way. Scientists suggest that every heavy element in the universe, everything heavier than iron in the periodic table, was made either in a supernova explosion or in the collision of 2 neutron stars, which is itself one of the most energetic events the universe produces. The gold in any ring you have ever worn, the iodine in your body, the lead in the earth beneath a road, all of it was produced in a stellar death and scattered into space and eventually gathered across billions of years into the cloud that became our solar system. The stars made these things, and then they ended, and the making travelled outward and found new shapes. What a supernova leaves behind depends on the mass of the original star. For stars in the moderate to massive range, what remains at the centre is a neutron star, a city-sized object of almost incomprehensible density, composed almost entirely of neutrons packed so tightly that a single teaspoon would weigh roughly 4 billion tons. Neutron stars spin rapidly, some of them hundreds of times per second, emitting beams of radiation from their poles that sweep through space like lighthouse beams, which is how they are detected and why a particular type is called a pulsar. For the most massive stars, not even the pressure of neutron degeneracy is enough to hold back the collapse. Gravity wins entirely, and the remnant collapses past any known stable state into a black hole, a region of space where gravity is so extreme that not even light can escape its pull. A boundary called the event horizon marks the point beyond which nothing returns. Inside, the laws of physics as currently understood cease to give reliable predictions. Black holes do not announce themselves with any visible sign. They are detectable only through their gravitational effects on nearby matter, by the light of material falling in and heating before it crosses the horizon, or by the gravitational waves produced when two of them merge. They are presences known entirely by inference, dark things made visible only by how they affect everything around them. What we understand so far suggests that stellar death is not an exception in the life of the universe, it is integral to it. The dying of stars is how the universe makes complexity, how hydrogen and helium, the only elements produced in significant quantity by the Big Bang, eventually become carbon, oxygen, iron, and everything else. How the interstellar medium is seeded with the raw materials of chemistry, how the conditions for biology eventually arise in the right place at the right time in a solar system that formed from the remnants of stars that had already lived and ended. We are downstream of stellar death. Everything about this planet, everything about the biology that walks and breathes and lies quietly in the dark, wondering about the stars, is made from the material of supernovae and stellar winds and the slow drift of planetary nebulae. Not metaphorically, physically, literally, measurably. The stars gave what they had, and what they had became everything. There is something the mind does with information like this late at night, when it is not trying to categorize or analyze. It simply holds it, lets it rest there alongside everything else, the weight of the blanket, the sound of the room breathing the particular quality of whatever darkness is outside the window tonight. The stars ended, and the ending made things. The things eventually made eyes to look back at the stars, and the eyes tonight are closing. The universe, it seems, has always been in the business of transformation. Not loss exactly, not ending exactly. Something more patient than either of those words. And the most patient transformation of all, the one that makes everything that came before it look almost brief, is only just beginning to come into view. There is a number that cosmologists use sometimes almost apologetically, because it is so large that it ceases to feel like a number at all. 100 trillion. Written out, it looks like this: 100,000 billion. A 1 followed by 14 zeros. In years, it represents a span of time so far beyond anything in human experience, or geological experience, or even the current age of the universe, that the mind, when it tries to hold it, tends to simply let it go. Not from lack of interest, but from a kind of gentle surrender. The way you stop trying to count individual stars and simply accept the sky as full. 100 trillion years from now, give or take across an enormous range of uncertainty, the last star in the universe will exhaust its fuel, and then there will be no new light. To understand what that moment might look like, or rather what it would not look like, since there will be no eyes to observe it, it helps to trace the slow path that leads there. Because the ending of stellar life in the universe is not a sudden event. It is a process that has already begun in a sense, and that will continue with the same quiet patience that characterizes everything the universe does on its largest timescales. The Milky Way is currently forming new stars at a rate of perhaps 1 or 2 solar masses per year. That sounds modest, and by the standards of the galaxy's past, it is early in cosmic history. Galaxies were forming stars at rates 10 or 20 times higher. What we understand so far suggests that the raw material for star formation, The cool, dense gas that collapses under gravity into stellar nurseries is being consumed without being adequately replenished. Galaxies are working through their reserves. This does not mean star formation will stop soon. On human timescales, on civilizational timescales, on timescales that dwarf all of recorded history, many thousands of times over the galaxy will continue producing new stars. But the direction is set. The rate will continue declining, not because something goes wrong, but because something simply runs out. Sometime in the very far future, estimates vary, but the general range is tens of trillions of years. The last regions of gas capable of collapsing into new stars will have either already done so, or will have dispersed and cooled beyond the threshold where gravity can gather them back into anything useful. The stellar nurseries will grow quiet. Not all at once, not with any announcement. One by one, the conditions for new ignitions will simply stop arising. The last star to form will almost certainly be a red dwarf. We established this already. Red dwarfs are the most common type, the most efficient with their fuel, the ones with the lowest threshold for ignition. When the available gas has thinned to the point where only the smallest, most modest stellar masses can coalesce from it, those will be the last to form. That final red dwarf, whichever one it is, will not know it is the last. It will simply ignite the way every star before it ignited through the same gravitational collapse and rising pressure and threshold-crossing fusion that has been happening since the first stars lit the early universe. It will begin its slow, careful burn, and the universe around it will be extraordinarily different from the universe we inhabit, but the physics of it will be exactly the same. Picture, if you're willing to let the image form loosely and without strain, what that universe might look like. The galaxies as we know them will no longer exist in recognizable form. Over hundreds of billions of years, the Milky Way and the Andromeda Galaxy, currently approaching each other at roughly 110 kilometers per second, will have long since completed their collision and merger, settling into a single larger elliptical galaxy that astronomers sometimes already call Milkomeda. Other nearby galaxies will have joined this structure, or been absorbed by it, or drifted away beyond any possibility of gravitational return. The stars within this merged galaxy will be far fewer than today. The brilliant blue-white massive stars will be gone. They lived and died within millions of years, recycling their material, contributing their heavy elements to the interstellar medium, and leaving behind neutron stars and black holes that continue orbiting in the galactic structure without producing any new light. The sun-like stars will also be gone. Their red giant phases completed their planetary nebulae, dispersed their white dwarf remnants, cooling in the dark. Even many of the red dwarfs formed early in the galaxy's history will have exhausted their fuel and faded. What remains burning with dim and patient light will be the youngest of the red dwarfs, those that formed late, when the gas was already thin and the galaxy already old. A sparse population of faint red points separated by vast dark distances, each one carrying the last warmth of active stellar fusion in a universe that has grown very quiet around them. Researchers have found through the mathematical modelling of stellar evolution that the last surviving stars will likely be red dwarfs with masses at the very lowest end of what can sustain fusion, perhaps 8 to 10% of our Sun's mass. These stars burn at the absolute threshold. Their cores are barely hot enough, barely pressurized enough to keep the hydrogen nuclei colliding with sufficient energy to fuse, and because they burn so carefully, so conservatively at that threshold, they last the longest of all. The smallest possible star burning at the lowest possible rate, sustained by just enough gravity and just enough pressure to keep the fusion going, that star will outlive everything else in the cosmos by extraordinary margins. It may be that there is something clarifying about this arrived at slowly in the dark. That the very quality which makes these stars invisible to the naked eye from Earth, their dimness, their modesty, their refusal to burn brightly, is precisely what allows them to outlast everything that outshines them. When the last of these stars finally reaches the end of its hydrogen supply, the process will be gentle. Red dwarfs do not become red giants in the dramatic way sun-like stars do. Their lower mass means they evolve differently. They may brighten somewhat as they age, growing hotter and bluer in their final billions of years, as the helium they have accumulated in their cores changes their internal balance. But they do not expand catastrophically. They do not shed outer layers in planetary nebulae the way the Sun will. Scientists suggest that the least massive red dwarfs will simply fade. The fusion will taper. The outward pressure will decrease, but slowly giving gravity time to compress the star gently, and the compression will generate some heat, but not enough for new reactions. The star will settle into something resembling a white dwarf, a helium white dwarf, dense and dim, no longer fusing, simply holding the last of its heat. And then it will cool over trillions of years, radiating its warmth into the surrounding space degree by degree in the particular patience of things that have no reason to hurry, growing dimmer as it grows cooler, eventually in the very remote future becoming something so cool and so dark that it no longer emits any light at wavelength the word light applies to, the last ember cooling in the dark. There is a detail worth pausing on here briefly and gently. By the time the last red dwarf fades, the universe will be approximately 10,000 times older than it is today. Everything that has happened in the 13.5 billion years of cosmic history, we are aware of the formation of the first galaxies, the slow evolution of stars across generations, the emergence of planetary systems and chemistry and biology and everything that biology has ever produced. All of that will represent roughly 1/10,000th of the universe's total age at that point. We are not late in the universe's story, we are extraordinarily early. The stelliferous era is still young, measured against its full extent. The stars burning tonight have been burning for only a small fraction of the time stellar burning will continue. In some sense, the most interesting chapters of the universe's luminous period may not have happened yet. They are still ahead in those trillions of years of red dwarf burning slow and dim, and patient in galaxies that have grown quiet around them. Evidence suggests this is simply the nature of a universe with the particular physical laws ours has. Not a universe designed for human timescales, or even for the timescales of the stars we can currently see. A universe with a much, much longer story than any of us were born into knowing. The last star. It is not a poetic construct. It is a physical prediction grounded in the same physics that explains why the sun rises, and why hydrogen fuses, and why the sky is dark between the points of light. Sometime in the unimaginably distant future, a small red dwarf in what was once a galaxy will complete its consumption of available hydrogen, and the fusion in its core will stop, and the light it was producing will fade, and the space around it will receive the last light it will receive from any active stellar source for a very, very long time. There will be no witness, no remaining biology to register the moment, no instrument to record it. Most likely instruments require maintenance, and maintenance requires energy, and energy will be very scarce in a universe whose last power source has just gone dark. The moment will simply happen. The way all the largest things happen without ceremony, without significance granted by any observer, in the deep and patient quiet of physics, following its own rules to their natural conclusions. And the universe will continue, different, colder, darker, but continuing. Because the ending of the stelliferous era is not the ending of everything. It is the beginning of something else, something the mind finds harder to picture, because we have no intuition for it, no evolutionary preparation for a universe without stars. But it is there waiting in the physics as patient as everything else the cosmos does. There is a quieter layer to all of this one that sits beneath the timescales and the stellar masses and the cooling curves, and that most people never quite reach when thinking about the end of stars. It has to do not with what the universe loses when the last light fades, but with what it keeps. What persists in the dark doing something the universe has never fully stopped doing since its first moments. Something that neither needs light to continue, nor ends when the light does. When the last red dwarf finally fades, that small, dim, patient star cooling into silence over trillions of years, the universe will not end. It will simply change what it is doing. This is one of the stranger things to sit with if you let yourself sit with it slowly. The universe, we know, the one filled with light, with stars, with the warm orange glow of distant galaxies in long exposure photographs, is not the only universe this cosmos will ever be. It is one chapter, a luminous chapter extraordinarily long by any human measure, but a chapter nonetheless. And after it closes, the universe continues into something quite different. Physicists who study the long-term future of the cosmos have given names to the eras that follow. Not poetic names, but descriptive ones, names that try to capture in plain language what the dominant physics of each period will be. What comes after the stelliferous era, after the age of stars, is called the degenerate era, and after that something stranger still. But the thread connecting all of it, the presence that persists from the stellar era through everything that follows, is something you have already encountered tonight briefly and directly, as the remnant left behind by the most massive stellar deaths. Black holes. They form throughout the stelliferous era as they do now. Each time a sufficiently massive star reaches the end of its fusion and collapses past the neutron star threshold, a black hole is born. Each time two neutron stars spiral together and merge under mutual gravity, the result can be a black hole. Each time the center of a galaxy accumulates enough mass in a dense enough region, and nearly every large galaxy, including our own, contains a supermassive black hole at its center, the black hole grows, feeding on whatever passes within its gravitational reach. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, contains a mass roughly 4 million times that of the Sun. The one at the center of the galaxy, known as Messier 87, made famous in the first direct image of a black hole's shadow captured by a global network of telescopes, in the year 2019 contains a mass estimated at 6.5 billion solar masses. These are not small objects even by astronomical standards, and they are patient. Whatever a black hole accumulates, it keeps. It does not burn through its contents the way a star burns through hydrogen. It does not evolve in the active sense that stars evolve. It simply is a region of space from which nothing returns, growing slowly when matter falls in, otherwise sitting in the dark with the particular stillness of something that has no need to do anything at all. After the last stars have faded, the universe enters a long period dominated by the remnants of stellar life. White dwarfs cooling slowly, neutron stars spinning down over billions of years as they radiate their rotational energy into the surrounding space. Brown dwarfs, objects that never quite accumulated enough mass to ignite into true stars, drifting in the dark, slowly cooling from whatever warmth they began with. Researchers have found that even these objects, dense and long-lasting as they are, will not persist indefinitely. White dwarfs will continue cooling over trillions of years, eventually reaching temperatures so low they emit almost no radiation at all. Neutron stars will slow their rotation to near stillness. The degenerate era, name for the quantum mechanical state of the matter in these objects called degenerate matter, will itself eventually end not through any dramatic event, but through the slow fading of every remaining light source, however dim. And then after everything that was once a star has either cooled into darkness or been consumed by something larger, What remains in the universe in any appreciable quantity will be black holes. This is the black hole era, and it is by the standards of what came before it almost incomprehensibly long. The stelliferous era, for all its trillions of years, will look brief in comparison to the period during which black holes dominate the universe. Scientists suggest that the black hole era extends from roughly 10 to the 40th power years into the future, a number so large it requires scientific notation to write, without filling a page, to somewhere around 10 to the 100th power years. That second number, 10 to the 100th power, has its own name, a Google. The universe of the black hole era will be extraordinarily sparse. The distances between black holes will be vast, measured in units that make even intergalactic distances feel intimate. The background temperature of space will have dropped to almost nothing within a tiny fraction of a degree of absolute zero. The cosmic microwave background radiation that currently fills all of space, the faint afterglow of the Big Bang still detectable with sensitive instruments today, will have stretched and cooled into wavelengths so long they barely qualify as radiation at all. What we understand so far suggests that this universe would be to any hypothetical observer the darkest and coldest and quietest environment the cosmos has ever produced up to that point. And yet, and this is the strange soft heart of this particular era, it would not be entirely static, because black holes, it turns out, are not permanent either. This was one of the most surprising theoretical discoveries of the 20th century arrived at by the physicist Stephen Hawking in the year 1974 through a careful application of quantum mechanics to the region just outside a black hole's event horizon. The prediction is known as Hawking radiation, and it suggests that black holes slowly, extremely slowly, leak energy into the surrounding space. The mechanism is subtle, and sits at the edge of what current physics can describe with full confidence. Near the event horizon of a black hole, the mathematics of quantum mechanics predicts that pairs of particles, a particle, and its corresponding antiparticle are constantly flickering into brief existence from the energy of the vacuum itself. This is not unusual. It happens throughout space all the time, and in most places the pairs simply recombine and disappear, leaving no net effect. But near an event horizon, something different can happen. One particle of the pair falls inward past the horizon into the black hole. The other escapes outward, carrying energy away from the black hole into the surrounding space. From the perspective of a distant observer, it appears as though the black hole itself is radiating, slowly releasing energy, gradually losing mass. The rate of Hawking radiation is inversely related to the mass of the black hole. Smaller black holes radiate faster. Larger ones radiate so slowly as to be essentially undetectable by any current or near-future instrument. A stellar mass black hole, one produced by the death of a massive star containing perhaps 10 to 20 solar masses, would take approximately 2 times 10 to the 67th power years to evaporate completely through Hawking radiation. That is a timescale that makes the current age of the universe look like a single breath. A supermassive black hole like the one at the center of our galaxy would take incomparably longer. The numbers involved become so large that even scientific notation begins to feel inadequate to carry them. But the direction is set, and in physics, as in so many things, it is the direction that matters more than the pace. Every black hole is radiating. Every black hole is on a timescale the mind cannot hold without losing mass, growing very slightly smaller, very slightly warmer. Because Hawking radiation increases as mass decreases, meaning that in the final stages of the black hole's evaporation, the process accelerates until at last the remaining mass reaches a threshold where the radiation becomes intense, and in a final brief flash of energy, the black hole evaporates entirely. Gone. leaving nothing behind except a pulse of radiation spreading outward through a cold and empty universe, carrying with it whatever information the black hole had accumulated across its entire existence. Though what form that information takes and whether it is truly preserved is something scientists are still exploring with great interest and no settled answer. Imagine if the image forms willingly the final moments of the last black hole in the universe. By that point, everything else will have been dark for longer than all of the stelliferous era combined. The white dwarfs will have cooled. The neutron stars will have stilled. The universe will be so cold that the temperature of empty space will be measured in fractions of a degree so small they approach the theoretical limit. There will be no light in any practical sense, no warmth, no chemistry, no movement of any kind except the slowest possible drift of particles, separated by distances so vast that the word lonely, if applied, would be insufficient. And then the last black hole, enormous, ancient, having consumed entire galaxies worth of matter, over an era stretching across numbers that have no names, will begin its final evaporation. The Hawking radiation will intensify as the mass decreases. The process which was imperceptible across googles of years will accelerate into something that happens over seconds, and in a brief, brilliant flash brief, only by the standards of what preceded it, which may itself have been billions of years, the last structured object in the universe will release its remaining energy into the surrounding dark, and then it will be gone. Evidence suggests that what comes after is not silence in the way a room is silent after sound stops. It is something more absolute, a state that physicists refer to as the heat death of the universe, though we will leave the full details of that for a little later when the mind has had time to settle further into the dark. What matters here in this moment is simply the arc, the long sequence of transformation that the universe moves through era by era, each one stranger and quieter than the last. Stars to remnants, remnants to black holes to radiation, radiation to something even simpler. The cosmos reducing itself with extraordinary patience from complexity towards something very close to nothing. Not nothing quite, but very close. The mind tends to want to grieve this a little when it encounters it. And there is something honest in that impulse, the recognition that what is being described is a loss of a kind, a diminishment of what the universe once was and will no longer be. That response is not wrong, but there is something else available too if the mind is soft enough to find it. Something in the extraordinary length of the process. The black hole era alone, if a consciousness could somehow persist through it, and observe its passage, would contain more time than has elapsed since the Big Bang by a margin so vast that the entirety of cosmic history up to now would be invisible at scale. The universe does not rush toward its quiet ending. It dwells impossibly long in each stage of its transformation. It seems that the cosmos, whatever its final state, is in no hurry to arrive there. And in a universe in no hurry, there is something that feels not consoling exactly, but spacious. Room enough for everything. Time enough for more than anyone has imagined. Even here. Even now. Even in the dark of this particular night, which is by any cosmic measure still very early in the story. And somewhere in all of this darkness, somewhere in the vast cold quiet that follows the last light, the strangest discovery is not what the universe loses when it goes dark, but what the human body has always quietly known about darkness. What rest actually is, and why the dark is not the absence of something good, but the presence of something necessary. That understanding has been accumulating in science for decades, and it begins as so many things do closer to home than the stars. There is a particular kind of quiet that exists at the edge of understanding. Not the quiet of an empty room, or the quiet of a night with no wind. Something more like the quiet you find at the boundary of what can be known, where the mathematics continues beyond the place where intuition can follow, and you're left standing at a threshold aware that something is happening on the other side of it, but unable to quite see in. Stephen Hawking spent much of his working life at exactly that threshold. In the early 1970s, he was thinking carefully, more carefully than perhaps anyone had before him, about what happens at the edge of a black hole. Not inside it, where the physics breaks down entirely and current theory offers no reliable description, but just outside, at the boundary, in the region where the gravitational field is so intense that space and time begin to behave in ways that require both general relativity and quantum mechanics simultaneously to describe. And in that narrow, strange region, he found something that no one expected. To understand what he found, it helps to know something about the nature of empty space. Because empty space, it turns out, is not actually empty. Not in the way the word empty suggests, not a simple absence of things. Quantum mechanics, which describes the behavior of matter and energy at the smaller scales, tells us that the vacuum of space is alive with activity. Pairs of particles, a particle and its corresponding antiparticle, equal in mass and opposite in certain properties, are constantly flickering into existence from the energy of the vacuum itself, existing for an extraordinarily brief moment, and then recombining and disappearing, returning their borrowed energy to the vacuum before any instrument could detect them. These are called virtual particles. They are not metaphors or theoretical conveniences. Evidence suggests they have measurable physical effects. The Casimir effect, observable in carefully controlled laboratory experiments, is one demonstration of the pressure these vacuum fluctuations exert between closely spaced surfaces. The vacuum is not nothing. It is a sea of perpetual invisible activity, operating below the threshold of ordinary observation, but influencing the physical world in ways that are real and detectable. This is the background against which Hawking made his discovery. At the event horizon of a black hole, that spherical boundary beyond which nothing can escape the gravitational pull, something unusual happens to these virtual particle pairs. In ordinary space, the pair appears and recombines almost instantaneously. But at the event horizon, the pair can appear at exactly the wrong moment, in exactly the wrong place, one particle on the outside of the horizon, one particle on the inside, before they can recombine the geometry of space near the horizon, curved so severely by the black hole's gravity that the concepts of inside and outside are themselves strained separates them. The particle that falls inside crosses the horizon and is lost. The particle that remains outside finds itself suddenly real, no longer virtual, no longer borrowed, but a genuine particle with genuine energy free to travel outward into space. And because energy cannot simply be created from nothing, the energy this escaping particle carries must come from somewhere. It comes from the black hole itself, from its mass, which by Einstein's relation between mass and energy decreases by a corresponding amount. The black hole, in other words, loses a tiny quantity of mass with every pair of virtual particles that is separated at its horizon. It is radiating, losing energy, slowly, almost imperceptibly, but consistently and in one direction, only toward less mass, toward less gravity, toward eventual evaporation. Hawking radiation is by any practical measure almost impossibly faint. For a black hole of stellar mass 10 or 20 times the mass of our Sun, the temperature of the Hawking radiation is a fraction of a degree above absolute zero. Cooler than the cosmic microwave background radiation that currently fills all of space, which means that right now black holes are not actually losing mass net. They are absorbing more energy from the background radiation than they are emitting through Hawking radiation. They are in the current universe still growing, however slightly. Only when the universe cools further, when the cosmic background drops below, even the Hawking temperature of these objects, which will happen as the universe continues expanding and cooling over trillions of years, will black holes begin their net evaporation. But the principle is established, the direction is set. Researchers have found through decades of theoretical work building on Hawking's original insight that the relationship between black hole mass and evaporation time is not linear. It scales as the cube of the mass. A black hole twice as massive takes 8 times longer to evaporate. This is why stellar mass black holes require timescales beyond anything the imagination comfortably holds, while the hypothetical microscopic black holes that may have formed in the early universe would have evaporated almost instantly. A black hole with the mass of our Sun would take approximately 2 times 10 to the 67th power years to evaporate completely. Written as a decimal, that number would require more digits than there are atoms in the observable universe. It is not a timescale that any word in any human language was designed to hold. And yet it ends. Every black hole given sufficient time ends. The final moments of a black hole's evaporation are among the most energetic events the physics of the far future has to offer. As the mass decreases, the Hawking temperature rises. The relationship is inverse, meaning smaller black holes are hotter radiators than larger ones. In the final fractions of a second of evaporation, the remaining mass is so small and the temperature so high that the black hole emits a brief intense burst of radiation across a wide spectrum of energies. Scientists are still exploring exactly what this final burst looks like in detail and what information it carries. This connects to one of the deepest unsolved problems in theoretical physics, the black hole information paradox. When matter falls into a black hole, does the information describing that matter, the precise quantum state of every particle, survive in some encoded form in the Hawking radiation, eventually to be released as the black hole evaporates? Or is it destroyed, violating a principle that quantum mechanics considers fundamental? Hawking himself initially believed the information was lost. He later changed his view. The debate continues among physicists, and the resolution when it comes will likely require a complete theory of quantum gravity that does not yet exist. It is one of the genuinely open questions, the kind that sits at the frontier of human understanding, and has no comfortable resolution yet. Which is at this hour not a source of unease, but simply a reminder that the universe is under no obligation to be fully understood. It keeps its depth patient and quiet regardless of how long we look. There is something worth dwelling on very gently in the image of Hawking radiation itself. Not the mathematics of it, not the equations or the Planck lengths or the temperature formulas, just the image. A black hole, the most extreme gravitational object the universe produces. Something defined entirely by what it holds, by what it will not release. A region where gravity is so absolute that light itself, the fastest thing that exists, cannot escape. And yet at its edge something is always leaving, always slipping away, not through the horizon, not by escaping the gravity directly, but through the more subtle mechanism of quantum fluctuation at the boundary. The vacuum doing what the vacuum always does, flickering with virtual pairs, but at the edge of the most extreme object in existence, and finding in that extreme the conditions for something to become real that would otherwise remain virtual. The universe finds the gaps. It moves through the margins. Even in the most absolute confinement, physics can describe something escapes. Something continues outward. The mind quietly registers this if it is allowed to, the way it registers anything that arrives softly and without demand. What Hawking radiation ultimately tells us beyond the physics, beyond the theoretical implications for information and quantum gravity, is something about the nature of persistence in the universe. Nothing lasts in its current form forever, not stars which burn through their fuel across billions of years, not white dwarfs which cool across trillions, not neutron stars which spin down across longer still. and not even black holes, those objects that seemed for most of human scientific history to be the one thing from which nothing ever escaped. Everything the universe builds, the universe also slowly, patiently, in its own time unmakes. This is not destruction in any violent sense. It is transformation at a pace so slow it makes all other natural timescales look hurried. The black hole does not explode, does not collapse, does not fail. It radiates. One quantum of energy at a time across spans of time so vast they exceed all prior cosmic history by unimaginable margins. It releases itself into the surrounding space as gently as anything the universe has ever done. A star spends 1 billion years giving light. A black hole spends a googol of years giving radiation so faint it is barely distinguishable from the background. Both are in their way a giving away, a slow and complete expenditure of everything that was accumulated, offered back to the universe that produced it. Psychologists often note that the human mind finds a particular kind of rest in the contemplation of processes that are complete arcs that, however long, have a shape. Beginning, middle, transformation. Not necessarily ending in any tragic sense, but arriving somewhere different from where they started, having moved through something real. The life of a black hole, traced from its formation in the death of a massive star, through its billions of years of silent waiting in the dark, through its unimaginably slow evaporation, via Hawking radiation, and finally to its brief terminal flash. That arc is complete. It does not leave things unresolved. The universe in its own time resolves everything. There is something in that which the nervous system can receive as a kind of permission. Not to rush, not to finish, not to resolve anything tonight, but simply to know that resolution happens, that the arc bends always toward completion, that nothing in the physical universe, not even the most absolute gravitational prison ever formed, persists in its current state forever. Everything changes. Everything moves, however slowly, towards something else, including right now the mind that is following this story, which is itself in its own small way moving, settling, releasing the particular tension that comes from holding things too tightly. It seems that the universe has always done this, held things with great force for very long periods, and then through some mechanism subtle enough to require quantum mechanics to describe, allowed them to slip away, allowed the energy to travel outward, allowed the mass to decrease, the temperature to rise, the final release to happen. Hawking found this at the edge of a black hole, but the principle, if you turn it softly in the mind without forcing it to mean too much, feels somehow familiar. The way very held things eventually gradually begin to ease. The way a fist held closed too long will open not all at once. Not in any dramatic gesture, but in the natural relaxation of something that has held long enough and is ready at last to let go. The universe in the end lets go of everything, not quickly, not without the patience of eons, but completely. Every star that has ever burned, every galaxy that has ever formed, every black hole that has ever consumed the matter around it, all of it over timescales the mind can only gesture toward rather than hold released, transformed, sent outward into a space that grows darker and colder and quieter with each passing era. What we understand so far suggests that after the last black hole has evaporated, after the last Hawking flash has faded into an expanding sphere of radiation that will thin and cool as the universe continues its expansion, what remains will be a universe of almost pure emptiness. A few elementary particles scattered across distances so vast that their separation is effectively infinite. A temperature so close to absolute zero that the difference is meaningful only in equations. And even then it seems the story is not quite finished, because there is one more layer to this, a final state that physics describes as the endpoint of all thermodynamic processes, a condition so absolute and so strange that even the word darkness feels too active to describe it. and understanding it even from a great distance, even in outline, only changes something subtle about how the darkness of tonight feels. Not heavier, not lighter either quite, just more familiar somehow than it seemed before. There is a word in thermodynamics, a branch of physics concerned with heat and energy, and how they move through systems that carries more weight than it appears to at first. Equilibrium. In ordinary life, equilibrium sounds like a good thing, balance, stability. The state a system reaches when competing forces have found their level. And in many contexts it is good: the equilibrium of an ecosystem, the equilibrium of a well-rested body, the equilibrium of a room at a comfortable temperature where no draft disturbs the air. But in the context of the universe's long-term future, equilibrium means something different. Something more final. Something that physicists have been quietly discussing since the 19th century, when the laws of thermodynamics were first being worked out, and one of those laws revealed something about the ultimate fate of any closed system that nobody had quite expected. The universe, it seems, is moving toward perfect equilibrium, has always been moving toward it, and when it finally arrives across timescales that make even the black hole era look brief, that equilibrium will be absolute, complete, and permanent. This state has a name. It is called the heat death of the universe. To understand what heat death means, it helps to begin with what physicists call entropy. Entropy is, in its most accessible description, a measure of disorder, or more precisely, a measure of the number of ways a system can be arranged at the microscopic level while still appearing the same at the macroscopic level. A glass of hot water placed in a cold room has low entropy in a thermodynamic sense. The heat energy is concentrated unevenly, distributed distinct from its surroundings. As the water cools, as the heat spreads outward into the room, and the room warms slightly, and the temperatures gradually equalize, the entropy of the combined system increases. The energy becomes more evenly distributed, less concentrated, less useful in the technical sense that useful energy is energy that can do work, that can drive processes, that can produce change. When the water and the room have reached the same temperature, no more heat flows between them. There is no gradient, no difference, no direction for energy to move. The system has reached equilibrium, and nothing more will happen to it thermodynamically speaking until something from outside disturbs it. Researchers have found that the second law of thermodynamics, the law that says entropy in a closed system always increases or stays the same, never decreases, is one of the most robust findings in all of physics. It has no known exceptions. It operates at every scale, from the microscopic to the cosmic, and it applies to the universe as a whole, which is by definition the largest closed system there is. The universe's entropy has been increasing since the Big Bang. Every star that burns, every black hole that evaporates, every photon that travels through empty space and red shifts to a longer wavelength as the universe expands, all of it is increasing the universe's entropy, spreading energy more evenly, moving always and in every process toward the final equilibrium. Heat death does not mean the universe becomes hot. The name is somewhat misleading, a relic of the 19th century framing of thermodynamics in terms of heat engines and steam. What it actually describes is a state of maximum entropy, a state in which all energy is distributed as evenly as possible throughout all of space, with no gradients, no differences, no concentrations of energy anywhere that could drive any process. A universe in heat death would be extraordinarily cold, colder than anything that exists today. The temperature of empty space right now, set by the cosmic microwave background radiation, is approximately 2.7 degrees above absolute zero. That is already cold beyond most human intuitions about cold. But as the universe continues expanding, the background radiation redshifts and cools further. By the time the last black holes have evaporated, by the time even their Hawking radiation has spread and thinned across a universe incomparably larger than it is today, the temperature of space will have dropped to a number so close to absolute zero that the difference is meaningful only in theoretical terms. And then, after the last particle interactions have occurred, after the last quantum fluctuation has settled, after even the protons themselves have had sufficient time to decay through whatever slow process governs their eventual dissolution, the universe will arrive at a state in which nothing changes because there is no longer any difference between one region of space and another, no gradient to drive a current, no concentration to disperse, no process to unfold. Just space at uniform temperature containing the last few stable particles scattered across distances so vast they will never interact again in any timescale physics can describe. The question of proton decay is worth pausing on briefly because it represents one of the genuinely open questions in fundamental physics, and it matters for the long-term story of the universe in a way that is rarely discussed. Protons are, as far as current experiments can determine, extraordinarily stable. Laboratory measurements suggest that the proton lifetime is at least 10 to the 34th power years, meaning that if you watched a single proton for that length of time, you would not expect to see it decay. This is so long that it exceeds the current age of the universe by more than 20 orders of magnitude. But many theoretical frameworks, particularly those that attempt to unify the fundamental forces of nature into a single coherent description, predict that protons are not perfectly stable. That eventually, given enough time, a proton will transform into lighter particles, releasing a small amount of energy in the process. The timescale is almost certainly longer than current experiments can probe directly, and scientists are still exploring which theoretical frameworks, if any, correctly predict proton decay and on what timescale, if protons do decay, and the theoretical arguments suggest they probably do, though the timeline remains uncertain. Then the last of the ordinary matter in the universe, whatever survives, the evaporation of black holes and the slow cooling of white dwarfs, will eventually dissolve into lighter particles, and those particles into radiation, and the radiation will spread and thin until even it becomes indistinguishable from the background. The universe, if this picture is correct, will eventually contain almost nothing at all. A few stable particles, electrons perhaps, and the lightest neutrinos separated by distances larger than the observable universe is today drifting in a space so cold and so empty that the words cold and empty no longer carry any particular contrast with what surrounds them. This is heat death, not a bang, not a collapse, not a dramatic ending of any kind, a drift, a settling, an arrival at the place thermodynamics has always been pointing toward, reached with the same unhurried patience that characterizes every large-scale process the universe undertakes. There is a physicist's way of thinking about the heat death that is worth receiving gently without pressing it too hard for meaning. The second law of thermodynamics is sometimes described as the arrow of time, the reason time feels like it has a direction, moving from past to future, from order toward disorder, from concentration toward dispersal. The reason you can tell a film is running backward when you watch a broken glass reassemble itself from its shards, or when smoke flows back into a chimney. These things do not happen in forward time because they would require a decrease in entropy, which the second law forbids. In a universe that has reached heat, death, maximum entropy, perfect equilibrium, the arrow of time effectively disappears. Not because time stops in any theoretical sense, but because there is nothing left to mark its passage. No process unfolding, no change occurring, no before and after distinguishable from each other. The arrow that pointed from the Big Bang toward increasing entropy, that gave time its direction and its felt quality of moving forward, arrives at a universe where there is no longer anywhere for it to point, What we understand so far suggests that this state once reached is stable, in a way nothing in the universe's current form is stable. The stelliferous era was stable for trillions of years, but it was always burning through its own conditions. The black hole era was stable for googles of years, but even that was always slowly evaporating. Heat death is the first truly stable state the universe will have occupied, the first state from which there is no further thermodynamic process to drive it somewhere else. The universe, after an almost incomprehensible journey, will have arrived at rest. There is something worth sitting with here quietly. Not as a lesson, not as anything that needs to be resolved or applied or remembered, just as something to hold for a moment in the dark. The universe has been moving toward rest since its first moment. Every process that has ever occurred, every fusion reaction in every star, every supernova, every galaxy collision, every quiet emission of Hawking radiation, from every black hole across eras, no language was designed to describe all of it, has been in the thermodynamic sense a step toward equilibrium. A step toward the state where everything is as evenly distributed as it can possibly be, where no corner of the universe holds more energy than any other corner, where the restlessness that began with the Big Bang has finally completely exhausted itself. It seems that the universe has, in some purely physical sense, always been trying to find rest, and that the entire history of stars and galaxies and chemistry and biology and consciousness is something that happened along the way in the extraordinarily long, extraordinarily complex middle passage between the concentrated energy of the beginning and the perfect equilibrium of the end. We are not the destination of that journey, but we are part of it. We are in a very direct physical sense part of the universe's long unwinding toward rest. And tonight, lying in the dark with the mind growing soft and the breath growing slow, there is perhaps something in that which does not need to be named to be felt. The universe is settling, has always been settling, and you in your own small and temporary way are settling along with it. Evidence suggests that the human body's experience of sleep is itself a kind of local entropy management, a temporary decrease in the brain's metabolic disorder, a consolidation, a quiet restoration of certain gradients and concentrations that the work of waking depletes. Sleep is not passive. The brain during deep rest is doing something, processing something, maintaining something that would otherwise deteriorate. But it requires the willingness to stop driving the processes, to let the activity slow, to allow the particular kind of settling that only happens when the system is no longer resisting its own tendency toward rest. The universe does not resist. It has never resisted. It has been settling with perfect patience since its first moment, and the settling looks from the inside like the history of everything. Every star, every world, every moment of awareness that has ever existed, all of it, the texture of a universe finding its way by the longest possible route toward the quiet it has always been approaching. The mind, it seems, has been keeping something still and patient all along, something that knows this settling recognizes it has been practicing it every night in the dark. And what the body does when it finally releases into sleep is not so different in its way from what the universe itself is slowly across its entire existence learning to do. Somewhere between the last star fading and the heat death of the universe there is a much smaller darkness. The one you are in right now, a room, a bed. The particular quality of night that has settled around you over the last hour or so, not the absolute cold of a universe in equilibrium, not the vast emptiness between evaporating black holes, but something immediate and warm and entirely familiar. The darkness of a body that has decided or is deciding to stop. This darkness is not passive. That is the first thing the science asks us to notice. What happens to the human body in the dark, What happens to the brain, to the nervous system, to the chemistry of every cell is not a shutdown. It is not an absence of activity. It is a different kind of activity, older than any other kind. The body knows more necessary than almost anything the waking mind does, and in some ways more complex than anything that happens in the light. Begin with the eyes closed and what the brain does with that signal. Neuroscientists have observed that when light levels drop a small cluster of cells in the hypothalamus, a region deep within the brain, ancient by evolutionary standards concerned primarily with the body's most fundamental rhythms, begins to change what it is doing. This cluster is called the suprachiasmatic nucleus, and it is in essence the body's master clock. It receives direct input from light-sensitive cells in the retina, calibrates itself to the cycle of light and dark in the external environment, and coordinates the timing of nearly every biological process in the body. When darkness arrives, the suprachiasmatic nucleus sends signals that begin a cascade of hormonal shifts. The pineal gland, a small structure near the center of the brain that Descartes once called the seat of the soul, not accurately but poetically begins releasing melatonin into the bloodstream. Melatonin is not a sedative in the pharmaceutical sense. It does not force sleep. It is more like a signal, a biological flag raised to announce that darkness has come and the body should begin preparing itself for rest. Core body temperature starts to drop slightly. Heart rate slows. The digestive system quiets. The muscles begin to release some of the tension they have been holding since morning. It may be that this sequence, this gradual biochemically orchestrated preparation for sleep, is among the most elegant things the body does. Not dramatic, not sudden, just a gentle coordinated transition from one mode of being into another. The circadian rhythm that governs this process is approximately 24 hours long, calibrated over millions of years of evolution to the rotation of the Earth and the daily cycle of light and dark that rotation produces. Researchers have found that the circadian clock is not simply a response to light, but a genuine internal oscillation, a biological rhythm that continues even in the absence of external light cues, running on its own, internal timing, self-sustaining through a feedback loop involving specific proteins that accumulate and degrade in a cycle that takes approximately 1 day to complete. This clock exists not just in the brain but in nearly every cell of the body. The liver has its own circadian clock, so does the heart, the lungs, the skin. What the suprachiasmatic nucleus does is coordinate all these peripheral clocks, synchronizing them to each other and to the external environment through light signals and hormonal messages. The body is not one clock, but a community of clocks all entrained to move together. When they move together well, when the darkness comes at the right time, when the melatonin rises at the right moment, when the body temperature drops as it should sleep, arrives not as a sudden event but as a natural continuation of the preparation. The boundary between waking and sleeping becomes soft. The mind drifts. The thoughts that were coherent become associative, then imagistic, then simply sensory. And then there is nothing, or rather there is something else, something that the waking mind has no direct access to. Sleep itself is not a single state. Researchers have found that across a typical night the brain cycles through distinct phases, each with its own characteristic pattern of electrical activity, its own physiology, its own function. The deepest phase, called slow-wave sleep or deep sleep, is when the brain produces slow synchronized electrical waves that ripple across its surface in coordinated patterns, quite unlike the fast irregular activity of waking. During this phase, the brain does something that was only fully understood in the last decade. It clears itself. A network of channels in the brain called the glymphatic system discovered and named relatively recently a system that had been present all along, but simply overlooked expands during deep sleep, allowing cerebrospinal fluid to flow more freely through the spaces between brain cells. This fluid carries away metabolic waste products that accumulate during waking activity, including a protein called amyloid beta, the same protein that when it accumulates in excess over years and decades is associated with certain neurodegenerative conditions. The brain during deep sleep literally washes itself, clears the debris of the day's thinking, reduces the chemical residue of all that electrochemical firing. It is maintenance. Real, physical, measurable maintenance, the kind that requires the waking work to stop before it can proceed. Evidence suggests that this glymphatic clearance is one of the most important functions of sleep, and one of the most compelling explanations for why sleep deprivation is so profoundly damaging. It is not simply that the tired brain works more slowly, it is that the maintenance has not been done. The waste products have not been cleared. The system is running on substrate that has not been renewed, in a space that has not been cleaned with chemistry, that has not been reset. A body denied sleep does not simply rest less. It accumulates. And a body given sufficient sleep, sufficient darkness, sufficient time in those deep, slow wave phases, that body clears what it needs to clear, consolidates what it needs to consolidate, repairs what can only be repaired in the quiet. There is something in this that the universe in its own way mirrors, not as metaphor exactly, but as structural parallel. The universe too accumulates entropy disorder, the gradual spreading of concentrated energy into ever more even distribution. And the universe too has a direction it moves in during its deepest rest toward equilibrium, toward the state where all the active processes have finally run their course, and what remains is simply the stable substrate. Sleep is the body's version of settling, the nightly equilibrium that the brain requires, the local heat death of consciousness that allows consciousness to return renewed. The other major phase of sleep, rapid eye movement sleep, the phase in which most dreaming occurs, does something different, and in some ways more mysterious. During rapid eye movement sleep, the brain becomes highly active, more active in some regions than during waking. The eyes move rapidly beneath closed lids, as the name suggests. The body's large muscles are almost completely paralyzed, a protective mechanism that prevents the dreaming brain from acting out its experiences physically. And the brain produces a neurochemical environment quite unlike any other state low in norepinephrine, which is associated with focused attention and stress responses, and relatively high in acetylcholine, which is associated with memory consolidation and the formation of new connections. Researchers have found that rapid eye movement sleep plays a particularly important role in emotional processing. During this phase, the brain revisits the emotionally significant experiences of recent days, not to replay them neutrally, but to process them in a neurochemical environment that is by its nature calmer. The reduced norepinephrine means the emotional charge attached to memories is somewhat dampened. The brain can examine what was felt without re-experiencing the full intensity of the original feeling. Some sleep researchers describe this process as a kind of overnight therapy. The brain sorting through what happened, deciding what matters, filing what needs to be kept, softening the edges of what was difficult. Not erasing, not forgetting, but integrating in the quiet what the waking hours could not fully absorb. What we understand so far suggests that the relationship between sleep and memory is among the most thoroughly documented findings in sleep science. During sleep across both slow wave and rapid eye movement phases, through mechanisms still being worked out in detail, the brain consolidates the experiences of the day into longer-term storage. Synaptic connections that were strengthened during learning are selectively reinforced. Information that was encountered briefly is either integrated into existing knowledge structures or allowed to fade. The sleeping brain is editing, curating, deciding through processes that are largely unconscious and entirely automatic what the waking mind will carry forward and what it will release. This is in its way one of the most generous things the body does for itself. It does not try to hold everything. It cannot, and it knows it cannot. Or rather, the biology of it has evolved toward a kind of elegant selectivity that serves the organism better than total retention would. The things that matter are kept. The rest is let go quietly in the dark without the waking mind being asked to decide. The darkness itself is not incidental to any of this. It is the condition. The melatonin cannot rise properly in the presence of bright light, particularly the short wavelength blue light that modern screens emit with such efficiency, which is detected by the retina's light-sensitive cells as strongly resembling midday sunlight, and which signals to the suprachiasmatic nucleus that it is not yet time to prepare for sleep. The glymphatic clearance happens primarily during deep sleep, which the body reaches more readily in genuine darkness. The emotional processing of rapid eye movement sleep follows a rhythm that depends on the earlier deep sleep phases having occurred as they should. The whole sequence is built around darkness, not as a backdrop but as an active requirement. The body does not merely tolerate the absence of light, it uses it. It has been using it every night of every human life for as long as humans have existed, for as long as any mammal has existed. The circadian biology that governs sleep evolved in a world where darkness came reliably every single day, and the organisms that learned to use it well survived better than those that did not. Darkness is not the absence of something good, it is the presence of something necessary. Scientists suggest that the experience of lying in a quiet dark room, the particular quality of stillness that arises when the body is horizontal and the visual system is no longer receiving input, activates the parasympathetic nervous system in ways that begin the physiological preparation for sleep even before sleep itself arrives. Heart rate variability increases slightly, which is a sign of greater regulatory flexibility and reduced stress response. Cortisol levels, which peak in the morning and decline through the day, reach their lowest point in the late evening hours. The muscles released from the postural demands of being upright begin the progressive relaxation that continues into sleep. The body, when given the conditions, knows what to do. It does not need to be told. It has been doing this for a very long time. There is a detail in the neuroscience of sleep onset that is in a quiet way one of the stranger and more interesting facts about the transition from waking to sleeping. As the brain moves from waking toward light sleep, it passes through a brief intermediate phase called hypnagogia. In this state, neither fully awake nor fully asleep, the normal boundaries between sensory processing and internally generated experience begin to blur. Images appear without being summoned. Sounds that are not present seem briefly real. The sense of the body's boundaries softens. Thoughts that were following logical sequences begin to drift into associative patterns, then into images, then into something that has the quality of experience without the structure of waking thought. The brain in this liminal state is releasing its grip on the mechanisms that keep waking experience coherent and bounded. The editor relaxes. The fact-checker steps back. The part of the mind that monitors for relevance and logic and social appropriateness goes quiet, and what remains is something more fluid, more associative, more closely related to the dreaming mind that lies just ahead. Many people, it seems, resist this. The waking mind trained for coherence notices when coherence begins to dissolve and pulls back toward clarity. But the dissolving is not a failure. It is the doorway. The universe, across its own unimaginably long settling, is also releasing its grip on coherence, on structure, on the complex arrangements of matter and energy that produce stars, galaxies, planetary systems, chemistry, biology. Releasing them not in grief, but in the patient physics of entropy, moving toward the equilibrium that has always been the direction. And the body every night does a version of the same, releases the structure of the day, lets the coherence soften, allows the complex energetically expensive business of waking consciousness to go quiet so that something more fundamental can proceed. Both processes, the cosmic and the personal, move toward the same condition. Not emptiness exactly, not loss, but a stillness that is its own kind of fullness, the fullness of a system that has finally for a while stopped requiring anything of itself. The last star will one day find that stillness, cooling slowly, fading gradually until the light it offers is too faint to warm anything and then gone. The universe will continue without it, moving through its long quiet eras toward the equilibrium it has always been approaching. And tonight, in a much smaller, darker mind that spent its day in motion, is approaching its own version of that same quiet. Not the quiet of ending, but the quiet of rest. The kind the body has always known how to find given the right conditions and enough willingness to stop resisting the direction things are already moving. The direction tonight is down, inward, still. And somewhere in the science of what the sleeping brain does in the glymphatic clearing and the memory consolidation and the emotional processing and the slow restoration of everything that the day used up there is a kind of story that mirrors in miniature the largest story the universe has to tell. A story about what rest makes possible, about what can only happen in the dark, about the strange necessary gift of stopping. And there is one more layer to all of this one that the science has been quietly building toward across everything that came before tonight. Something about where the atoms in a breathing body actually came from. Something that changes in the softest possible way what it means to lie in the dark and look up at a sky full of stars, or to simply know they are there even with the eyes closed. Part 11. We are made of starlight. The last thing to remember. Word count 3150, duration 21 minutes. There is a fact in astrophysics so well established, so thoroughly verified across so many independent lines of evidence that it has moved beyond the category of discovery into something closer to the category of known landscape. It is taught in introductory courses and referenced in advanced research with equal casualness, and yet for all its familiarity within science, it has a quality when received slowly in the dark without rushing toward its implications that resists becoming ordinary. Every atom in your body heavier than hydrogen was forged inside a star, not metaphorically, not approximately, not in a poetic sense that dissolves under scrutiny. The carbon in every cell of your body, the oxygen carried in your blood with every breath, the nitrogen woven through your proteins, the calcium in your bones, the iron at the center of every hemoglobin molecule carrying oxygen from your lungs to your brain and back. That iron was made in the nuclear furnace of a massive star dispersed into space, when that star ended its life in a supernova and eventually incorporated into the cloud of gas and dust that collapsed 4.5 billion years ago into our solar system. You are not like the stars. You're in the most literal physical sense available to science made of them. To understand how this happened, how the interior of a star became the interior of a body, requires tracing a path that spans most of the universe's history and crosses distances so large they are best not measured in any unit smaller than light years. The Big Bang, as best as current cosmology can determine, produced a universe composed almost entirely of hydrogen and helium with trace amounts of lithium. These are the lightest elements, the simplest possible atomic structures. Hydrogen is a single proton with a single electron. Helium is 2 protons, 2 neutrons, 2 electrons. These are the raw materials the early universe provided. Everything else, every element beyond lithium in the periodic table, every atom that makes carbon chemistry possible, every atom that makes water possible, every atom that makes biology in any form possible, had to be made somewhere by some process, after the Big Bang. The universe did not begin with the ingredients for complexity. It began with the ingredients for the first generation of stars, and it was those stars burning through their hydrogen, and then through subsequent fusion processes that built the heavier elements one by one. Scientists call this process stellar nucleosynthesis. It is in the broadest sense the reason chemistry exists at all. The first stars in the universe formed from the pristine hydrogen and helium of the early cosmos, before any heavier elements had been made anywhere, were almost certainly very different from the stars we see today. Evidence suggests they were likely massive, burning hot and fast-living only a few million years before ending in supernovae that seeded the surrounding space with the first heavy elements ever produced: carbon, oxygen, silicon, iron. Scattered into the interstellar medium mixed with the remaining hydrogen and helium, they became part of the raw material for the next generation of stars. Each generation of stars built on the chemistry of the previous one. Each supernova enriched the surrounding gas with heavier elements that the next generation incorporated at formation. Over billions of years, the interstellar medium, the gas and dust between stars, gradually accumulated a richer and richer mixture of elements, the product of countless stellar lives and deaths, each one contributing something to the growing complexity of what the universe contained. Our Sun is by this reckoning a third-generation star or later. It formed from material that had already been processed through multiple cycles of stellar birth and death. The heavier elements in its composition, and by extension, the heavier elements in the planets that formed around it, including this one, are the accumulated product of all those previous stellar generations. The inheritance of billions of years of nuclear alchemy carried forward from star to star across time. The carbon in a human body is worth dwelling on for a moment because carbon is the element that makes biology as we know it possible, and its origin is one of the more remarkable stories in nuclear physics. Carbon is produced in the cores of stars through a process called the triple alpha process, in which 3 helium nuclei called alpha particles in nuclear physics fuse together in a very specific sequence to produce a carbon nucleus. The remarkable thing about this process is how improbable it seems on the surface. The intermediate step, the fusion of 2 helium nuclei into beryllium, produces a beryllium nucleus that is extremely unstable, decaying back into 2 helium nuclei in approximately 100 millionth of a billionth of a second. The window in which a third helium nucleus can arrive and complete the fusion to carbon is extraordinarily brief, and yet it happens, constantly in the cores of red giant stars across the universe. The reason it is possible at all has to do with a quantum mechanical resonance in the carbon nucleus, a specific energy level that allows the 3-body fusion to proceed at a rate high enough to produce significant quantities of carbon. This resonance was predicted theoretically before it was measured, because a physicist named Fred Hoyle reasoned that if carbon exists in abundance in the universe, and if we exist, then the carbon nucleus must have this resonance. It must. Because without it, we would not be here to notice its absence. The existence of carbon, and therefore of carbon-based life, depends on a specific quantum mechanical property of a single nucleus. The universe produced that property, and the stars used it billions of times over to build the carbon that eventually found its way into every living cell on this planet. Researchers have found that the iron in human blood is particularly ancient by stellar standards. Iron is, as noted earlier in this story, the element at which stellar fusion stops producing energy, the endpoint of the nuclear burning sequence in massive stars. The iron in a star's core is not freshly made. It is the final product, the ash of all the previous fusion stages accumulated, until the core becomes too heavy to support itself and the star collapses. When that collapse triggers a supernova, the iron, along with all the other elements synthesized in the star's core and outer layers, is expelled into space at velocities of tens of thousands of kilometers per second. The shock wave of the explosion compresses nearby gas clouds, often triggering new rounds of star formation. The iron disperses across light years of space cools, and eventually over millions of years settles into the diffuse cloud of gas and dust that will one day become part of a new solar system. The iron in your blood followed exactly this path. It was made in a stellar core. It was expelled in a supernova. It drifted through interstellar space for millions of years. It was incorporated into the solar nebula that collapsed into our sun and planets. It became part of the early Earth. It entered the chemistry of life when life began. And it has been cycling through living organisms on this planet ever since, through oceans of ancient bacteria, through the bodies of creatures that lived and died long before anything resembling a human existed, through the food that built the cells that built you. It is very old iron, among the oldest atoms your body contains, older than the solar system, older than the Earth, made in a star that lived and died before our sun was born. This is not a small thing to hold in the mind even softly. The body that is lying here in the dark, breathing slowly, that body is assembled from the histories of multiple stellar lives. The hydrogen in its water is primordial, made in the first few minutes after the Big Bang, 13.5 billion years old. The carbon in its cells was made in a red giant star perhaps 8 or 10 billion years ago in the triple alpha process. The iron in its blood was forged in a supernova scattered across space, waiting in the interstellar medium for millions of years before the sun formed and gathered it in. The oxygen that enters with every breath was made in the cores of stars that lived and died before this solar system existed. Nothing in the body is new in the cosmic sense. Everything was somewhere else first, doing something else for an almost incomprehensible length of time, before becoming part of this particular arrangement that is right now warm and breathing and drifting towards sleep. Psychologists often note that the human sense of self, the felt experience of being a continuous bounded individual, is so robust and so constantly reinforced by experience that it can be difficult to genuinely hold alternative perspectives on what the self is. The boundaries feel real. The sense of inside and outside feels absolute. The experience of being a particular person in a particular body in a particular place feels like the most certain thing there is. And yet the atoms that compose that body have no loyalty to it. They arrive from elsewhere and will leave for elsewhere. The carbon that is currently in a cell of your lung was a year ago part of a molecule of carbon dioxide in the atmosphere. 5 years ago, it may have been part of a plant. 50 years ago, part of a different person, or a different organism entirely. The atoms cycle through bodies the way water cycles through clouds and rivers and oceans, continuously, without preference, without memory of what they have been. What makes a body is not the atoms themselves, but the arrangement, the pattern, the specific, improbable, extraordinarily complex organization of matter that constitutes a living system, and within a living system, a nervous system capable of experience, capable of lying awake at night and wondering about the stars it is made of. The arrangement is temporary. It has always been temporary. It will eventually dissolve and the atoms will go on as they always have, cycling through other arrangements, other forms, other configurations of matter in a universe that recycles everything it has ever made. There is something that the mind does with this information when it receives it in the right state, not the state of analysis, not the state of trying to draw conclusions, but the soft state, the late-night state, the state in which the boundary between what is inside and what is outside feels slightly less absolute than usual. In that state, the fact of being made from stars does not feel like a piece of trivia. It feels like something else, something harder to name but easier to feel, a kind of continuity with the very old, a participation in something that did not begin with birth and will not end with death. but that moves through those moments the way a river moves through any particular stretch of its banks, present and passing and continuing. The atoms were in stars. They are briefly in you. They will be in something else after. The universe does not lose them. It simply reassigns them with patience and without preference to whatever arrangement needs them next. What we understand so far suggests that the oxygen entering your lungs with every breath has been breathed by other organisms for hundreds of millions of years, cycled through the atmosphere fixed by photosynthesis, released by respiration in a continuous loop that predates multicellular life. The nitrogen in your proteins was fixed from the atmosphere by bacteria that lived in soil and ocean sediments long before any animal existed. The water in your cells has been rain and ocean and glacier and cloud and river more times than any number could capture. You're not separate from the world. You're in the most physical and measurable sense available a temporary local organization of the world flowing through itself in the particular shape of a body for the particular duration of a life, borrowing its atoms from the larger cycling of matter and returning them when the borrowing is complete. And those atoms, before they were part of the world, before they were part of any planet or ocean or living thing, were in stars. In the nuclear fires of stellar cores, or in the expanding debris of stellar deaths, or drifting through the cold interstellar medium between one stellar life and the next. The stars did not just give light to the world, they gave the world its matter. They gave every living thing the atoms it is made of. They gave you specifically, and without knowing it, every atom that is currently here in the dark, breathing, warm, heavy with the beginning of sleep. It seems that the connection between a body lying in the dark and the stars above is not poetic. It is not a metaphor chosen for emotional effect. It is simply what the physics describes, followed all the way from the beginning of stellar nuclear synthesis to this moment in this room, with the breath slowing and the mind beginning its own kind of drift. You are the universe observing itself, not in a grandiose sense, not in a way that requires any particular feeling to be attached to it, simply in the sense that the matter that was once in stars has through an unbroken chain of physical processes spanning billions of years arrived at an arrangement that is aware of where it came from, and tonight that arrangement is resting. Returning for a few hours to something closer to the undirected state of matter, the complex organization of waking consciousness, releasing its grip the way all complex organizations eventually do, into something simpler and quieter. The stars spent themselves to make you possible, and tonight you're doing what the stars do in the end, letting the light go quiet, settling into the dark that was always there, that will always be there, that holds everything that has ever shone and everything that will shine again. And what comes after this, what the final settling feels like from the inside of a night that is already almost over, is something that needs no more science to describe. Only the particular quality of a voice going softer and words going fewer, and the space between thoughts growing gently, gently wider. That is where we're going next, and it is not far. There is a moment just before sleep fully arrives when the boundary between thinking and dreaming becomes too soft to locate. You are still aware in some sense, still present. But the thoughts have changed their quality. They have become less like sentences and more like images, less like arguments and more like weather. Something is happening, but it no longer requires your attention to continue. It is carrying itself forward the way a river carries itself without needing anyone to push it. That moment is worth noticing if you can notice it without disturbing it, because what the neuroscience tells us about that threshold, that hypnagogic borderland between waking and sleep, is that the brain has in a very real sense decided to trust the dark, decided that the monitoring can stop that. The vigilance that has been running quietly in the background of every waking hour can be set down, not permanently, not in any final way, just for now, just for the night. The body knows how to do this. It has been doing it for as long as bodies have existed, and everything that needs to happen in the dark, the clearing, the consolidating, the restoring, all of it will proceed without any effort from you, without any direction, without anything being required except the willingness to let the transition happen. And tonight there is something additional worth carrying into that threshold, something the last several hours have been quietly building toward without ever quite stating it directly. You're made of material that was present at the beginning of the universe, not similar material, not material of the same type. The actual atoms, the specific configurations of protons and neutrons and electrons that constitute the molecules of your body, have been part of this universe since shortly after it began. The hydrogen in the water in your cells has been hydrogen since the first few minutes of cosmic time nearly 14 billion years ago. It was there before any star existed, before any galaxy, before any structure of any kind had formed from the formless expanding heat of the early universe. And the heavier atoms, the carbon and oxygen and nitrogen and calcium and iron, those were made in stars as we have travelled through tonight, forged in stellar cores across billions of years of cosmic history, scattered in stellar deaths, gathered into new clouds, compressed into new solar systems, incorporated into planets and oceans and the long patient chemistry of biology until they arrived here, in this body, in this particular arrangement that is for now you. Researchers have found that the atoms in the human body are replaced on average over periods ranging from days to years depending on the tissue. The carbon in your body's molecules cycles through on timescales of months to years as food is consumed and metabolized and the molecular structures of cells are continuously rebuilt. The calcium in your bones turns over more slowly over years. Some atoms stay longer, some pass through quickly borrowed for a season and then return to the world to become part of something else. But while they are here, while this particular collection of atoms is arranged in this particular way, holding this particular temperature and electrical activity and chemical complexity, what we understand so far suggests that this arrangement is in the entire history of the universe unrepeated. The specific configuration of matter that constitutes a conscious, breathing, experiencing body is not something the universe produces in bulk. It is something that emerges slowly under very specific conditions over enormous timescales, and then exists for a while and then disperses back into the larger pool of matter that will go on to become other things. The atoms do not end when the arrangement ends. They never end. They simply change what they are part of, what they participate in, what story they are briefly inside of. There is a quality of connection that this fact offers if you let it arrive slowly enough to be felt rather than just understood. Every star that has ever burned, every red dwarf burning patiently in the dark right now, every massive star that exploded billions of years ago and scattered its elements across a spiral arm of a galaxy, every one of those stars contributed in some small way to the material that eventually became you. Not metaphorically, through an actual chain of physical processes, measurable in principle, traceable through the isotopic signatures that different stellar environments leave in the elements they produce. You are downstream of all of it, of the first stars that ignited in the young universe burning pure hydrogen and helium into the first carbon and oxygen the cosmos ever contained, of the supernovae that seeded the interstellar medium with iron and calcium and all the heavier elements, of the quiet solar wind that carried material from our own sun into the outer solar system and back, of the impacts and the volcanism and the chemistry that cycled elements through Earth's crust and oceans and atmosphere for billions of years before any biology existed to use them. All of that history is in a very literal sense inside you, carried in the atoms, written in the isotopes, present in the structure of every molecule in every cell. Scientists suggest that the feeling of smallness that often comes with contemplating the scale of the universe, the sense of being diminished by the comparison, is not the only response available to this information. That alongside smallness, or perhaps beneath it, there is something else, a sense of participation, of being genuinely part of something, not as a metaphor but as a physical fact, made from the universe's own material, running on the universe's own energy, subject to the same physics, the same thermodynamics, the same long, slow arc toward rest that every other thing in the cosmos is subject to. The universe is not something separate from you looking down at you from a great distance. It is something you are made of, something you are continuous with in both directions of time, backward to the first moments, forward to whatever the atoms will be part of next. This is not a comforting thought in the way that comfortable thoughts are comfortable. It is something quieter than comfort. More like the feeling of a hand placed gently on a shoulder, not solving anything, not changing anything, but acknowledging something, a presence recognized, a belonging without sentimentality in the oldest and most physical sense of the word. The last star, when it finally fades, that small red dwarf burning alone in a universe that has grown very quiet around it, will not end the story of the atoms it is made of. Those atoms will continue. They will drift slowly through a universe growing colder and emptier with each passing era. They will be subject to the same forces that have always governed them. They will not know what they were part of, but they will have been part of something, part of the stelliferous era, part of the long luminous chapter of cosmic history in which the universe burned with enough energy to make chemistry possible, and chemistry became complex enough to make biology possible, and biology became organized enough to produce something capable of lying in the dark and wondering about the last star. That is not a small thing. Even in a universe of unimaginable scale, even measured against timescales that dissolve all human reference points, the fact that the universe produced wonder at itself, that the atoms arranged themselves briefly into something that looked up and asked questions, is not nothing. It is in some quiet way the most interesting thing that has happened so far. The darkness outside your window tonight is full of light that is old and patient and still travelling, full of stars at different stages of their long lives burning with the same physics that built the atoms in your body, full of space that is expanding slowly and continuously, carrying everything further from everything else in the long drift toward equilibrium that began before any of this existed. And the darkness in this room is also full of the particular chemistry of a body preparing for rest, full of the slow activity of a brain doing its nightly work, clearing, consolidating, processing, restoring, full of the breath that moves without being asked to, full of the heartbeat that has been keeping time quietly and without interruption since before you were born. Both darknesses are doing something. Neither one is empty. The breath slows. The thoughts, if there are still thoughts, have grown lighter, less insistent. The body has been making its preparations for a long time now, since the light first changed this evening, since the melatonin first began its quiet rise, since the temperature first began its gentle drop. It has been moving in this direction all along. Everything has been moving in this direction. The atoms are old. They have been many things. Tonight they are this warm, breathing resting, part of a small arrangement that will not last forever, but that is right now entirely real. The stars are out, some of their light left before any human word existed to describe it. It is still travelling. It does not need to arrive anywhere in particular. Somewhere a red dwarf is burning, dim and steady, patient in the way that only very old, very quiet things are patient. It does not know it is the last of anything, it simply burns. The universe continues, slower now, darker now, but continuing. And here in this room, in this body, in this particular arrangement of atoms that the universe has briefly loaned the shape of a person, the breath moves. In, out. The thoughts grow soft. The dark holds everything gently. There is nothing that needs to happen now. Nothing to understand. Nothing to remember. Only this. Only the quiet. Only the dark which has always been here, which was here before the first star, and will be here after the last, and which is in its own patient way enough.